If you've ever felt intimidated by deep learning research papers with their dense mathematical notation and complex code bases, this comprehensive tutorial will show you how to effectively understand and implement cutting-edge AI research. Through practical examples using recent papers, you'll learn the three essential skills needed to master deep learning research: reading technical papers, understanding mathematical notation, and navigating research code bases. Yassine teaches this course. He's a published researcher and machine learning practitioner.
Deep learning research might look daunting to get into, especially if you don't have a strong theoretical background in deep learning. It's fast-paced, full of abstraction, and mixes advanced math with advanced programming. In this tutorial, I'll show you the basic of how to start understanding deep learning research, which include the theory, the math, and the code. Unfortunately, these type of techniques aren't really taught formally, and you kind of just need to figure them out on your own. For those that don't know me, I'm Yassine, a published researcher and machine learning practitioner who love to teach. What we'll learn today is broken down to like 3 specific skills. So you have reading research papers, understanding mathematical notation within these papers, and reading deep learning code bases. For this tutorial, I'm assuming that you have at least some understanding of what machine learning is about. So if you are more an early beginner, I do recommend like these freeCodeCamp tutorial to start out. They are great. We will use 2 recent papers throughout the tutorial to give you like some good practical examples, namely QHAdam, which is a type of deep learning optimizer, and the segment editing model, which is a segmentation model from Meta. I will use that last one at the end of this tutorial to showcase like how you can summarize the finding of a deep learning research paper using the 3 skills we learned. By the end of this tutorial, you should be better prepared to read pretty much any deep learning paper. So let's start with how to read a research paper and understand the theory. The cutting-edge deep learning research is usually packaged into these papers. These articles are a bit atypical in the sense that they are very information dense. The general idea is that by studying an article, you should be able to reproduce fully an experiment, which, by the way, is super hard to do. So if you want to understand the cutting-edge theory, you need to be able to read effectively a research paper. In this section, I'll show you my framework to read these in the most cost-efficient manner. To start out, there are 2 ways to read a paper, depending on your goals. The first way is to kind of understand what was done, but not in depth. Usually to use the result of the research or to understand another paper using these results. This way of reading relies heavily on trusting that the paper is right. It's not too difficult to do. If you read the abstract and conclusion of a paper, you can get the gist of it. It's a bit like knowing roughly what React is doing, but being more interested in using it than understanding how it's implementing like a shadow DOM. The second way to read a paper is where people get lost. The goal is to understand a research project so deeply that you can reproduce these results. In that setup, there is little trust and you actually need to understand the paper methods. This way of reading paper is what I'll be covering today. Before we start, let me preface it with a warning about deep learning research in general. It's a highly empirical field, meaning a lot of things get discovered just because they were tried. It also means that whenever reading a deep learning paper, you need to understand the context in which it was written. Most of the stuff used within can be slightly wrong, or at least the reasoning for why they worked is wrong. Be acutely aware of that. You will see it's easier to see it with very old deep learning paper with the knowledge that we have currently. Okay, so the full method I use looks somewhat like this. There's like 7 steps. I involve like multiple read, 3 of them, which is very normal for any research paper. Paper in general are not linear. They are kind of a structure with like a lot of interdependency. The first step to read a paper is to have enough contextual information about it to be able to orient yourself properly. Going into a new field is highly disorienting. If you don't have context, you will get lost. Researchers with lots of experience within the field already have the context, so this is why they can grasp a paper easily. My favorite technique to absorb all the context before reading a paper quickly is the following. I find like 2 or 3 blog posts summarizing the main finding in the paper. It don't have to be well written or right. It will just help me orient myself with the nomenclature and stuff like that. After that, I find like 5 or 10 diverse video on the paper main findings. Again, you are going for a diverse set of opinion about what is important in the paper. I will suggest here to vary the length, so between like 6 to 60 minutes is good. The first material you will ingest on the paper subject will feel disorienting. However, after a few, you will start to notice patterns that will tell you where the real focus of the paper lies and where the strengths are. This will also mean that as you read more paper in the field, it will get easier and easier to absorb the context faster. Now that you have the context in your head, you can open up the paper for a first casual read. I first start with a linear read from end to end, where I note down on a separate sheet every element that I don't understand. Everything I understand is all fine usually. I keep reading over it. I don't research things I don't understand deeply while I'm doing my first read, I just make note of them. There are usually 5 things in a paper that I take note of that make it harder to understand. These are unknowns I need to somewhat categorize and elucidate to make sense of the whole research. The first category of unknowns are critical elements of the paper that aren't explained by the others and implied to be understood. The second type are critical topics that are explained in the paper but need some work to grasp fully. The third type of unknown are elements that the author didn't understand fully, so they kind of waved it away. This type of unknown is usually very hard to get an answer for and is a core target for criticism in later years following publication. The fourth type is surprisingly stuff that the authors got wrong. It does happen. It doesn't mean the paper is garbage though. Sometimes things works out anyway. The fifth type is element of the paper that the reviewers wanted to be added before publication but provided no value whatsoever to the paper. These usually sticks out of the paper. Once you're done with noting down all of the unknowns, you're ready to start to fill some gaps. Try to categorize the stuff you didn't understand into these 5 categories. Only tackle the external unknown for now. Research whatever you don't understand and make sure you come back to the paper with a better understanding. Don't get too lost here. If it's a bit specific method the paper make use of, leverage the first way of reading a paper, which is to superficially understand the intuition behind, or better yet, just read a blog that condenses the technical information that you need. Okay. Now comes the second read-through. The whole purpose is to reduce the number of internal unknown to the minimum. In that read, I like to do the following. Start with the abstract and the introduction to understand what is a setup in the paper. Try to understand the paper's motivation because it will help with understanding why the methods are the way they are. Then you jump to the discussion and conclusion section at the end of the paper to see the end point of this experiment. It's important that you understand deeply what the author got out of the research. Generally, the conclusion will follow the motivation of the start in a connected fashion, since the paper was not written introduction first and then 6 months after that they got to the conclusion. It was all written like together in a recursive fashion. Finally, I take each of the figures out and I try to understand what everything in the figure means. The axis, what the graphs are highlighting, the units, all of this stuff. At this point, I feel a very deep connection with the whole research. I use the introduction and the conclusions as anchor and try to fit in the result shown in the figures in a sort of like logical timeline. If there is something that feels disconnected, it's a hint that there is maybe something else that I didn't understand apart from the specific method or result the other got. Now there are 2 ways to finish up the second read-through. Reading through the technical details slowly and making sure you understand each step conceptually, including the formulas, or you open up the code base for the paper first, if it's provided, and start mapping out each of the sections. I like the second way because as a software engineer, it will give you confidence that this stuff is not magic. At the end of the day, it's code that was written up and ran to generate whatever results. Do a good pass on the code base until you feel kind of comfortable about where things are and that you cross-reference some of the name in the code with those in the paper. Disclaimer though, research code is usually very messy and doesn't have a standardized structure. Keep that in mind. So we're going to check out how to read a codebase in the last section of this tutorial. You'll see it's not that complicated. You just need to explore the codebase progressively across many abstraction layers. Once done with the code, you're ready to check out the methods result section in depth. Go slowly and carefully and understand the methodology behind the paper step by step. There are a few repeating elements in a deep learning experiment that are mostly always there. Understand that structure helps a lot in knowing how to navigate the method section. First, there's the data that is fed to the deep learning model. The data has a specific structure that dictates the architecture choice for the model. As you dive into a specific field, you will see the same kind of data set used over and over again. Then there's the architecture of the model per se. Here it's the layer used, the connection within said layer, and all this. There might be a lot of different sub-elements in an architecture that you don't necessarily understand at first, and it's okay. After that is the type of gradient descent optimizer and training regimen used. There are a lot of empirical details usually hidden in here, so it's fine if the why isn't always 100% clear in the training. Finally, there is the pipeline from the raw data to whatever result is generated. Sometimes paper will combine multiple architecture in specific ways, like with an ensemble method. In any given research, there are usually only a few tweaks that understand the core. As you read more paper, you will start to spot them easily. Break each of the steps from the method down and try to understand the logical flow. If something feels weird or surprising, check the code or other resources for reason why the author did it the way they did. Finally, go slowly through the results section and fill in the blank in your timeline between the introduction and the conclusion with the numerical or qualitative result. And once done, I usually like to do a final read from start to finish and look at my note to ensure I understand completely the flow. Again, if there is something that feels weird during that read, it might be that I still don't understand something explained within the paper, or that the author didn't explain something fully for a literal lack of knowledge, or that the author was flat out wrong, or that the reviewer asked to add some superfluous garbage information which feel disjointed. Anyway, in all cases, after this third read, you should understand the paper enough to take on a reproducibility effort if needs be. So, understanding the theory at the high level is very important. A lot of the deep learning concept will be packaged and reused in different research in various configurations. This theory is what orients you in the practical implementation within the codebase. However, you still need to be able to read the mathematical notation to have a truly well-grounded intuition about why things work. It's a fundamental aspect of deep learning theory. Reading deep learning math may look intimidating, but it's not that difficult. You just have to take your time. In this section, I'll show you my framework for reading math that I use when I encounter a very densely packed section of formula in a paper. We'll be using the quasi-hyperbolic momentum paper, so QHAdam, to showcase the method. The method I use has these 5 steps which we will go through. The core idea is that you need to slow down when you read math in deep learning paper and work through the formula by hand. So let's get started by taking a deep breath. Feeling overwhelmed by math is completely natural. This feeling is experienced by many others, even seasoned machine learning practitioners. First thing you should realize though is that you're supposed to take one glance at the formula and get it, especially if the formulas have arbitrary single letter names like X, A, B. What you're supposed to do is you work through the formula and understand each of the elements that compose it and make multiple attempts at understanding how everything connects together. At the end of this exercise, you should be left with an intuition about why something is working. That intuition is what you will be recalling next time you see the formula. But first off, take a deep breath. Now that we have the right mindset, the first step is to identify all the formulas in the paper that are shown or referred. The ones that are shown in the paper should be kept within their logical block. What I mean by that is that each of the formula blocks are trying to come down to a result of some sort. Identify these groups of results. Sometimes it's not too clear, so do your best. The one that you need to make sure you track down and note are those that are referred in the paper but not shown. Those are usually a good source of confusion since the others will assume you know what they mean already. Also, be aware that the later formula usually connects logically to the one shown prior in the paper. Once you identify all of them, I would strongly advise you to take them out of the digital world into the real world, aka on a piece of paper. This might be just a personal preference, but I've always found that you need to have as much degrees of freedom as possible to move around math. The variables aren't just variable, they mean something. Being able to take your pen and sketch out the motion the formula is going through, or how a variable refers to a specific topic, is critical for your understanding. Prepare to work on the formulas just as you would a Lego building set. After you took all these formula out, now is the time to translate the symbols you are seeing into meaning. Math is as much about symbols as a poem is about letters. The meaning behind the symbols is absolutely crucial for you to get at a deep level to be able to read the formula. The best way I found to parse math when encountering a new formula is to slowly and surely study each of the symbols and understand their interaction together. Here's how I do it. We'll use this formula from the quasi-hyperbolic Adam paper. I'll show you an overview and then I'll work through it myself. First, I want to understand what each of the individual symbols means and put a name on them. Just in this example, there are 12 symbols that we need to understand, which aren't explicitly explained in the image. As you work through this first step, you will realize that a lot of the formulas are reusing the same symbols. Hopefully, they are not changing their meaning within the same paper. When reading them from now on, name them in your head instead of reading alpha or epsilon or beta. After that, I look at the connection between these different entities and how this interaction is transforming some things with one meaning into a completely new one. This is where I do a lot of the work to build out an intuition. Take example, and work through them to really unveil the motions these ideas are going through. Finally, I then study how each of these individual ideas construct to the final result for a logical block. Ideally, at the end, I should be able to rock someone or rub a duck on how we're going from these atomic entities to these larger concepts and how they all connect together. This can take a while, by the way, especially if I'm missing core concept that I need to fetch externally. All right, let's jump into the formula now and work through the core one we just saw so that you see how it's done. So remember the first step, like not freak out. So we're going to be reviewing this paper, Quasi-Hyperbolic Momentum in Adam for Deep Learning. We're not going to actually review the paper, just the formulas. This is a cool one because it looks scary, but it's actually pretty simple. And there's some information that is not in the paper, so you have to get it out. So we're going to go through the whole flow together. But first thing first, we take a deep breath. This is not that hard. You see here we have some formulas. You see we have another formula here, right? And then there's a whole bunch of them, and we have the big one, which is this scary one, right? All the mumbo jumbo. So let's get to it. Okay, so step one now, we have to identify all the formulas that are shown and referred. So the first one that we have here is not an actual formula, it's kind of like a template, right? But it's important to know it's this one, like definition of optimization algorithm, and then you have that thing, right? So like the parameter at time t plus 1 is the parameter at time t minus something. So this is cool with this paper is that they really break it down from like very like the primitive to the actual novelty. So let's take it out and put it into our stuff. Next one we have is the plain stochastic gradient descent, which is just over here. It's also pretty simple. So we have like this minus alpha times this stuff. Second one we have is this momentum version of the stochastic gradient descent. Okay, so we're making some good leeway right now. Then we get the first thing, which is the quasi-hyperbolic momentum. So this is not the QHAdam, it's the QHM. And here we are starting to get a lot of letters, but it builds up into the thing that we've seen before. Let's take it out. Okay, afterward we have a whole bunch of stuff. They're doing comparison between that thing, QHM, with like Nesterov, accelerated gradient, PID control. We have a synthesized Nesterov variant, an accelerated stochastic gradient descent, a whole bunch of them. We don't need to dive into them. Basically, they're making the claim that like QHM recover all of them. If you change the parameter properly, this is not too important, so we skip them. Then we get to QHAdam, which is where things get a bit out of control. So let's take this whole thing out and let's stop a bit here. Let's look at our flow. We're starting with the primitive, and then we have this one, the stochastic gradient descent. We have the momentum one, cool. We have the QHM. So far, everything makes sense. Then we jump straight to QHAdam, right? So it's the QHM thing applied to Adam, but they haven't mentioned Adam, so we need to get that out. And this is external to the paper. So here we are in the Adam paper. So this is the original one. And then we have this beautiful algorithm that walks us through like the whole thing that we need. So we can use this one. And there we go. Now we have the whole gang. The whole gang is there. We have this one, Adam, and then we have QHAdam. Job's done. Okay, now ideally you take these out and you're gonna like take them out of here and start to work on them on a piece of paper like I'm doing over here. Reason for this, right, like I said prior, is that like I don't have a lot of degree of freedom here. Like I have my mouse here, crappy mouse, and I'm gonna write like this and I'm gonna work on them. I much prefer have like my ends and then try to like circle stuff and then like name something here, take another piece of paper and try to do like some derivation if I need to, and then bring it back and then have all of my stuff on the table that I can move around and look at it, right? Like for demonstration purposes, I'm gonna do it all over here, but ideally I just took them out already and I worked through them on a real piece of paper. Okay, so let's work through this piece of alphabet soup. So what we have here, if we start with the QHAdam, you're gonna freak out. Like for sure, you're gonna freak out. Like what the hell is happening here? We have like these ones, like are these derivative? No. Like we have g t plus 1, s t plus 1, you have s here. You have a bunch of variable beta. This look important. This look like a hyperparameters, right? And you have these on top, the v's that we saw previously. But this thing absolutely unreadable. Like this is total madness. So the trick, right? If you have a whole flow, a paper that will do the whole flow and the whole journey, there's a reason behind it. There's a reason why in the paper this is like section 5 and not section 0, right? So take a step back. Okay, here we are. Took a step back, right? We start with the primitive here. We have theta, which is the model parameters, right? So every time we're going to see a theta now, don't say theta in your head, say parameter at t plus 1 here. Parameter at t plus 1 is equal, right, to the parameters at time t minus something. That's how you should read it. So now we know what theta is. Then we have the L of theta. And what this means is that it's just a loss function to be minimized via the parameters that we have. So the L in everything that we're going to see, we should say in our head loss function. Then we have L hat, because if you see all of them, like they have a little at on them. There's never like L alone. And this is the little thing that will confuse you. Like you have L of theta hat. What the heck does that mean? It's like, it just means that it's an approximator of the loss function, right? So over a mini batch, that's all it means. So if you were coding this thing, you are giving a mini batch, right? So like about 50 or whatever thing. And then through this, you average them out. And then this is how you make a step for the parameter through that mini batch. You don't take the whole of the data set every time to make like a thing. So this is why it's an approximation of the loss function. You're kind of approximating that this is the number for the loss. In some cases, if you're doing like literally stochastic gradient descent, you're going to take one of the data points. Okay, so we're good. Now what the heck is the little triangle inverted L, right? It's the gradient of the function L. Again, you're never going to see that. You're not going to see the gradient of L. You're going to see the gradient of here, L hat of approximation, because you're taking one simple data point or multiple at time t. So just with this, you have 4 different symbols, but this is what it means. It's like, it's an approximation of the gradient at time t. Okay, we're making some headways here. Like all of these stuff, right? It's already like a whole bunch of the unknowns that are kind of put out. But you have to kind of stop and then really put in your head what all of these means. And then you have the vectors are operation or element wise, good. And then you have blah, GS, VW, like all of these are auxiliary buffer, right? So what it means, a buffer in programming sense is just like an array of some sort where you're going to store something like in between X number of steps, right? You see here, like there's 2 steps. So this is one buffer, right? Here there's like 2 buffers because you have multiple steps, and you have all of these which are related, right, to these buffers. So there's operation on buffers that are happening. Okay, so we know. So whenever we see G, S, V, W, and even A sometimes, they're going to be auxiliary buffer. And G is special. It's the momentum buffer. We're going to see it also in momentum again. You see here? It's over there. Finally, all of these stuff are subscribable by T, which is a step in time for the optimization. So good job. Now we have like a good understanding about what the heck is happening. We can move one step further into our road to understand QHAdam. So here we have the stochastic gradient descent, the plain one. So if you see that, we have the parameter at t plus 1, right, is equal to the parameter at time t minus, right, you see, same form, alpha time the gradient of the approximator of the loss with the parameter theta at t. So what does that mean? Let's break it down a bit, right? So this is the parameter, the current one here, that we jam, and then we're going to calculate the approximation of the loss function, and we're going to take the gradient of that. So this we know. And then there's this A here, right? Here this is an alpha actually, it's not the A that is here. And alpha we're saying here that is called a learning rate. And this is just a hyperparameter that you can tune so that you can take small step or big step. So that's it. The only thing that is new here is this learning rate. So now every time we're going to see alpha afterward, we're going to keep in mind that it means the learning rate parameter, right? And if we see a A instead, maybe a buffer. We're good. Here we got stochastic gradient descent, and let's also not forget the form that this thing is taking, right? Like the form, I feel, is almost as important as a symbol as soon as you have the idea in your head. Now when I'm gonna see this, right, this thing, for me is telling me like this is an optimization step that I'm taking, right? So if I see the same form somewhere else, I'll know that this is what they mean. Let's look at the momentum, for example. You see, if I just glance over these two formula, this one and this one, I know for sure this is the optimization step, right? It's the same form as this one over here and the same form as this one. The other one is not the same form. It's something else, right? But you see that this one thing is connected to that. So now we recognize the form that it's taking, and we see that there's some stuff that are added. We still have our learning rate here, right? We still have our good old parameters over here. We have G, which is now called the momentum buffer, right? And then we have B, which is called the exponential discount factor B, beta actually. So this thing is now the exponential discount factor in my head. And what is happening here, right? If we have a beta of 0, so this gets killed out, and this goes to 1, right? We just recover the stochastic gradient descent. So there seems to be like a weighted average between two things, right? Here it's between this, which is the gradient of the estimator of the loss for the parameter at t, right? And this other thing, which is what? This other thing is what happened previously. So the previous buffer, right? So what it effectively is doing is it's taking into consideration the previous optimization we've done. If it was super big before and now it's super small and the beta is controlling, like let's say it's at 0.9, what you will do is you will take into consideration what was happening before, right? But dampen it down just a bit. So this is how effectively you're getting this ball to be rolling. Because in this case, right, if we had a big optimization step at t minus 1, and now we're at time t, and the step is small, we're going to go big step, and then we're going to go small step, right? It doesn't matter. It will move. If you see it in your head, it will move like kind of in a stop motion type of way. You can have a big motion and then small motion, big motion, medium motion. It doesn't matter what happened previously. Here though, it's not this. It's taking into consideration what happened in the past. So if the past was big, right, and technically this step should be small, it would actually take this one and this one. So it will still be big. It will still be a big step, a bit lesser than this one though, right? It will be maybe something like this, right? And then if all the steps that we calculate are still small, it will go gradually slower and slower and slower. So now in your head, your intuition, you kind of understand why this is called momentum. Because it's literally, if you see the parameter as a ball that is rolling through this lost landscape, it actually has a momentum. It has some prior acceleration from before, and there's some friction in this plane. Okay, so now you take a good snapshot of this, right? Because it will have the same form with QH momentum. Okay, so we have the two together. This was the stuff prior, and this is now QHAdam, right? Let's just take a look at it. And if I had them on paper, I would just like take a look at them like one after the other. If you were to superimpose, you have the B, GT here, same thing. You have 1 minus B, same thing. Like the first one, the G T plus 1, so this momentum buffer is exactly the same thing. There's nothing has changed here. This is good. We know what this means. What is happening here that is different is this whole part, right? Remember when I said that this is kind of an average weighted of two things? It's doing the same trick again, right? This thing is the weighted average between this quantity, right? Which is very similar to this, right? But it's this quantity, which is something, plus the rest here, which is what was before, right? So what is going on? Effectively here, we have, how they call the V? The V they call an immediate discount factor V, right? So it's a weighted average of the momentum update step and the plain stochastic gradient update step. Let's take a look back at stochastic gradient descent. So here we are, we have both of them. You have stochastic gradient descent here, and then we have momentum here. What the V is actually doing, right, is it's going to take an average between what is happening if we only were following stochastic gradient descent for now, and then what will happen if we were only following the momentum step, right? Because momentum is this, and stochastic gradient descent is this. So this is what this means, right? There's nothing inherently complicated here that is happening. We're either going to follow momentum more or like stochastic gradient descent more, and we're going to keep those two things running in parallel. That's it. That's all that QHAdam is doing, essentially. There's nothing more fancy than this. That's the whole idea. And it explained it in the paper. But when you see it here, it also becomes very, very obvious. So now we're getting there. Let's move into Adam. And if you take something out of the paper, right, from another one, you have to be very careful about like the variable. These variable will not be the same most likely than the other ones that you just saw. So you have to take this idea and maybe rewrite it a bit, and then you can incorporate it back into your stuff. So let's take a look at this. You can see right now it's a bit different. It's not an actual formula, it's an algorithm, right? So the other decided to do it this way instead of having a formula. So you have to be aware that there's going to be some slight difference and be flexible. So here, step size, this is like our alpha, so it's also the learning rate. You have B1, B2, which is our exponential decay rate for the momentum estimate, right? These B's are the same, these betas are the same betas as in the momentum, but you have two now. So you have F, which is a stochastic objective function with parameter theta, which should be L in our case. You have theta, which are the parameter vector. This is good. There's a moment vector 1, and then there's a second moment vector. So there's two moment vector. In the momentum, you have only one momentum vector. T is the same thing. So now what we see, we calculate the gradient, and then we calculate the two momentum vector at the same time. The momentum vector will have a specific formula. This one, same thing as before, right? Nothing different here. This one is different because we're taking g at exponent 2 at t. So it's at gt and at gt exponent 2. That's all there is. That's the only difference between the two. Then it does something a bit different. It's doing a bias correction of the first moment estimate and a bias correction of the second moment estimate. So in those two things, they are corrected before getting implemented into the formula. So this is why you're going to see 4 buffer, right? You have the 2 buffer because you're just adding one more than the momentum. And then you're going to take these two, correct them, so that these matters, not the other ones anymore. And then you take these two quantity and then you jam them into the update rule. And the update rule, if you look at it, take a look quickly at it, you see the same thing, right? You have previous parameter, some learning rate, and something, whatever it is, right? It's just that in this case, it's this bias corrected first momentum divided by the square root of the second momentum plus some epsilon, which is usually some error that you're gonna use to not have to divide by 0 if this thing is way too small. You see here, it's very small. And that's kind of that. That's the form of Adam. Now you know it, right? Keep it in your head before going into the other stuff. Okay, now we're ready for QHAdam. So if you take a quick look over here, yes, there's a lot of letters, but one thing to notice is that it's the same stuff here as Adam. If you were to rewrite this stuff, the first 4 buffers, exactly the same. So if you work through this, you understand pretty well what is going on here, right? Where the difference lies is over here, right? You see, we have the exact same idea of QHAdam. If you look back at QHAdam, you see we have the idea of like the parameter v, which is the immediate discount factor that is oscillating between two things, right? In this case, QHAdam, it's either stochastic gradient descent if v equals 0, or momentum if v equals 1, and you can have like a continuous type of stuff between one or the other. It looked like it's the same thing in QHAdam, but not exactly, right? Because if you take a quick look, we have v1 and then we have v2, right? So if I had like on my piece of paper, what I would do here is I would try a bunch of a variation of these to understand what actually the algorithm is doing. So, but like here, they will already tell you if you have v1 and v2 equal 1, right? You get Adam back, because if you have that, this will go to 0, so this is knocked out, this is knocked out, this doesn't exist anymore because it's a 1. So you have the first momentum buffer divided by the square root of the second momentum buffer plus an epsilon. That's directly Adam. It's the same thing as here, this thing over there. So it shows that like with these parameters, you can recover a lot of different algorithm, and then you can have like a continuous quadrant, let's say here, right? Based on the value of v and the value of v1 and the value of v2, right? And on each extreme, you're gonna get something different. So here you can, with QHAdam, you can recover RMS prop if you set v1 to 0, right? And if you set v2 to 1, right, you're gonna recover MRS prop. If you do v1 equal beta 1 and v2 equal 1, you're gonna get NADAM. And then you can get like a whole bunch of these like that. So that's kind of this is the idea, right? The idea is that instead of having like only one algorithm for optimization, it's mixing the power of multiple ones in order to create something that is a bit different. And if you look at the experiment section in the paper, it shows like why it's better, more efficient, and whatever. But if we only look at the formula, that's basically it. That's the exact same ideas as before, right? For QHM applied to now two axes, essentially. And that's it. Now that we did all that work of understanding, I would distill down each of the logical formula into an intuition that you understand. Very important here. You don't need to be mathematically rigorous in your intuition. You just need to make logical sense for you. Write that down in the paper, and now you can break through the paper from start to finish. And if need be, you can always go and dig back down to follow your train of thought that led to this intuition. Sometimes, even when you take your time to read the mathematical formula, you might still feel like you're missing the basics. Having the right technique to read math isn't a substitute to studying math effectively and understanding it. A strong mathematical foundation will enhance your understanding of pretty much anything you will encounter when studying the cutting-edge deep learning research. In this segment, I'll show you my framework to study math and why it's set up in a very exercise-driven approach. If we take a sneak peek at the process for mastering deep learning math, it's actually very simple. I'll show you all the details in a few minutes, but we'll start first with an exploration of why there is a high emphasis here on doing exercise. This process applies to any kind of math, but for deep learning math, you need to put a focus on very specific subfields. So, my conclusion here is that to get good at math, you need to do math. So the reason I'm making this statement is because I've subjectively found it through practice that it is the best way to learn. So I tried a lot of different ways throughout my studies, during my undergrad, master, PhD, and the only one that I found that reliably work is to actually do the math. And here, I'm not talking about attending classes or watching lectures or taking very detailed notes. All that is frankly optional. I'm literally saying that the only way for it to click in your head is to take the pen and then do the exercise. So check out what Grant from 3 Blue 1 Brown, which has a very popular YouTube channel for math visualization, think on the subject. It will echo a bit the same exercise focused approach to math learning I'm going to show you here.
What is the best way to learn math for people who might be at the beginning of that journey?
Your temptation will be to spend more time watching lectures or reading. try to force yourself to do more problems than you naturally would. That's a big one. Like the focus time that you're spending should be on like solving specific problems, and seek entities that have well-curated lists of problems. So if you can, take a little look through those questions at the end of the chapter before you read the chapter. A lot of them won't make sense. Some of them might, and those are the best ones to think about. A lot of them won't, but just, take a quick look and then read a little bit of the chapter and then maybe take a look again and things like that. And don't consider yourself done with the chapter until you've actually worked through a couple exercises.
Okay, so assuming my subjective experience and Grant one is correct, that you in fact need to do math to get good at math. Why though? So why math is like that? Like why it stands out compared to other discipline like biology, which you can master by kind of just learning the facts. So this meta-review paper in the psychology field called The Connection Between Spatial and Mathematical Ability Across Development shines some light on the matter. So there seems to be like a deep link between spatial ability and mathematical ability across a whole range of age group. So if you look over here, like they've done a bunch of meta review of different paper. And here the average age was 5, 6, 12, 19, 21. And then they measure like math skills of different sort. One of the interesting conclusion of this paper is this one. And the author said, we also find evidence of strong spatial mathematical connection and transfer from spatial intervention to mathematical understanding. Spatial ability and math are related in their cognitive process in some kind of sort of way. You might stop here and wonder like, hey, I'm good in physical activity, which are spatial in nature, and I still suck at math. So the logical conclusion here, in my view, is very simple. So you aren't thinking about math or training it either in the right way. So let's take a look at two spatially related skills, like one fairly obvious, you'll see, and one a bit less so, and how to get better at them to get a sense of their parallel with math.
The team, go sports!
So the first spatial related skill is obviously sport. To get good at any sport, you don't probably reach out to a textbook or a lecture or watch like tons of video about it. You actually need to do the sport first and foremost to get good at it. Even if your understanding about why a certain set of movement works is incomplete, you can still be very solid at that particular sport. Sure, you need to have like the right muscular endurance to be able to do these movements and all that, but past that, you need to be able to focus your brain to do the movement properly. So if you were to kind of mindlessly do the movement without thinking about them correctly, you might either hurt yourself or have mediocre performance at best. Therefore, to be good at sport, you kind of need to do quality reps that engage your spatial function of your brain properly, and lots of them. So this is where the mastery comes from.
Spades. 6 of spades.
2 of hearts.
Okay.
Jack of spades.
The second spatial related skill is, surprisingly enough, memorization. It's a bit of a tangent here, but for mammalian and human more specifically, there's a very deep connection between our spatial ability and memory. There's a very tight connection between having good ordered recall memory and spatial visualization. There's a whole bunch of different ways to memorize. Let's say something complicated like the periodic table. You can do rote memorization, you can try that, where you try to name the element like one by one and then you repeat that. Or you can link the element together into like some sort of visualization that link them together in a sort of big chain. That's another one. But the more potent methodology here is the memory palace method. This method, which I studied while I was doing research in a psychiatry lab, leveraged one of the core aspects of the human brain, which is that you are very much able to remember hundreds, if not thousands, of ordered elements automatically and effortlessly. So if you were to close your eye right now, right, and think about your kitchen, right, think about the kitchen, you wouldn't just like blank out and not know where the heck the stuffs are. And like, if there was something surprising in the kitchen, like a kangaroo, you'd be like, what, why is a kangaroo over there? If you don't have a kangaroo. So in your mind eyes, you will be able to look around everywhere and tell me exactly where everything is to varying degree of details. So the method of loci hijack that fact and take the random element order that you are trying to learn and put them into a path of your own choosing through familiar places. So the repetition you need to do for memorization is, funnily enough, not in the object you're trying to memorize per se. The objects are kind of irrelevant, they can be anything. It's in the spatial area and in the visualization you're using to encode the elements in space that take most of your time. So the repetition, once again, need to happen thoughtfully in the spatial domain to have a mastery over this memorization ability. Here, I'm making the non-scientific argument that the reason you need to do a lot of math to get good at it is because it is very much like these other skills, which requires leveraging the innate spatial power of your brain. So a bit of a detour here, but we are finally there. So let me show you what my technique looked like after having refined it throughout the years. You see it's pretty simple. First, you need to select the right subfield of mathematics to study. So not all of them are directly relevant, and some of them might become relevant in very specific subfield of deep learning. But the broad category are the following four. So our good old calculus, followed by linear algebra. Then you have the frequentist probability and the Bayesian type of probability. There are plenty of others, the whole field of complexity. But if you get a solid mastery of these four, there isn't anything outlandish you will encounter in deep learning. It's mostly just that. Now, within these subfields, you need to find resources that are very exercise rich. If you are aiming to actually understand the material at a deep level, you will need to do your repetition and you will need lots of them. So find a good textbook or some sort of repository of exercise with their answers. Take all of these elements and put them into a gigantic list that you will be referring to. The method I found that worked the best to structure the repetition is what I call the green, yellow, and red method. I don't even know if it's an official name, but I call it that. So the method is very simple. You start with any of the exercise in your list. It really doesn't matter which one you start with because you're going to literally drill them all multiple times. So you do each exercise while trying to do the following. You try to focus on visualizing the shape of the problem and the motion to get to the right answer. So at first, you aren't going to visualize much and you will feel kind of awkward and forced, just like absolutely any movement you ever attempted for the first time in your life. So once you try the exercise, look directly at the answer to get feedback. So, did you get the right answer? If yes, and you understand why you got it right, congratulations. You put a green on this exercise and you will never do that one again. People might disagree here, but there is no point of doing it again because you managed to go through the motion first try. So with more skills and understanding, this exercise will be trivial and a waste of your time and energy. So I would focus most of my time on the harder exercise. You're gonna see that's kind of what this method does. So if you messed it up and you understand the motion that you messed up, you put a yellow on this and you move on. A yellow means that you're going to come back to this one in your next pass. So if you messed it up and even with the answer next to you, you have zero idea what the heck is going on, you put the big fat red next to it and you just move on. Red means that you're going to dig a bit more in the theory and drill this exercise multiple times because there's a critical part of the motion you do not understand. This or the shape of the problem, you can't see it. I like to do these passes by groups of subjects. So this way, if a whole subject is green, I'm just not going to even take a look at it anymore. I will focus on the harder problem for my understanding. So the visualization part you need to perform here is broken down into two parts. So the first part is what is the shape of the problem you are trying to solve? And the second is what are the motion to go through to solve these particular type of problem? A very good mental model to understand this shape, pattern, motion type of thing I'm talking about is mountain climbing. For a novice, the mountain look like one big difficult element to climb. It's just you have to climb that thing. But when you hear a master of this thing like Alex Honnold talk about the mountain, it's very clear that it's actually not one thing. It's few big problems that are broken down into a set of movement in between them that the guy actually drilled multiple times. The big problem are the shapes that you need to recognize in the problem statement, and they are very much just pattern you need to learn about. And sometimes the problems are bigger, but they contain different shapes within them that require different sort of movement. So the motion and the movement that you will need to perform match how the problem gets solved. Now the cool part, once you're done with the first pass, you do another one and you only do the yellow and red. So for these, do study the theory before attempting them again and look at various examples so to make sure that you got it right. So whenever I study a theory, I put heavy attention on the motion that is going on and I try to find resources that are very heavy on the visualization to supplement it. So again, 3 blue, 1 brown, master at that and make complex topic very understandable. At this point, I keep track of the yellow and red in the pass, and rule of thumb, I like to do at least 2 passes here when I get a yellow, just so I don't just memorize the answer at the end, but I understand the motion. And if I get a deep red, I do the maximum of 5 pass, just so that I can understand the theory and the reason why I didn't get it at first. After 5 pass, usually I understand all problem and all the motions. So if you look here, you're gonna do try 1, you're gonna do all of these exercises, right? Try 2, you're gonna do a few less, and then every try that you're gonna do, It's going to be less and less, but only those that like you don't actually understand. And this is where you're going to learn the most, because at some point you're just going to be drilling the stuff that is still unknown to you, how to go from the shape of the problem to the actual motion that you need to do. It's kind of it, folks. Like there's not anything more than that. You just drill problem until you get this problem shape pattern recognition, and you can start to kind of feel the motion that you need to go through. So just like a gymnast that is able to do a complicated like aerial movement, you'll be able to do calculus, linear algebra, or probability, and understand intimately the movement in your own spatial brain. A strong theoretical and mathematical understanding is crucial to get a solid grasp of advanced deep learning topics. However, to truly understand the full extent of deep learning research, you need to be able to dive into the code base and following what is going on. The code is kind of an extension of the paper, especially like in deep learning, which is a very empirical field. By understanding the implementation, you'll get a strong intuition about why the author structured their method in a certain way. In this section, I'll show you how I go about reading a deep learning codebase by using the segment anything model as a basis. The very first prerequisite step is to read the paper thoughtfully to get all the contextual information. This might look obvious, but it has to be said. If you just read the blog or skim through the abstract, you'll miss critical context and implementation detail that stem from the codebase. Read the paper fully at least once and take notes of the various nomenclature used throughout. The next step is to try to make the code run using the provided documentation. Usually, deep learning code will have like enough information in the README so that you can properly run a model on some test data. It might not always be straightforward because of the complexity of research code. However, it's well worth it to get a top level sense of the input, output, how the system kind of manage these and what it requires to functions. Let's see how this looks like with SAM1. We're gonna check out this repository. As I said, I chose this one mainly because the code is clean. It's very clean and it's cutting edge. It's like, well, it was cutting edge in 2023, but now this has been superseded by Segment Anything 2. But still, the code is very clean and it's well thought of. So first thing first, we're gonna try to make this run. How we're gonna make it run is we can like install this whole stuff locally. I like to, if I'm just testing stuff out, just go into like Colab or like whatever other engine that is online and do the work of setting it up over there, so I don't have to mess around with a lot of stuff and GPU and all this. So the first thing we're going to do here is we're going to install a Segment Anything, the library that we just saw. Over there you see that they added two things, the people.jpg, this image of me in a poster presentation, and then the parameters from this model, which is the Segment Anything model with the visual transformer, the H version. So this is just to showcase it. We're going to store this into the image variable. Over there, we are going to use the sum automatic mask generator. And here are our parameter that we need. It's just like how this code is set up to load it from the parameter. We put it over there, put this into a GPU, and over here we're creating the mask generator. At the end over here, we are using the image, and then it can generate a mask. Here, it's not too important, it's just to take the mask and then be able to showcase an image. And here we are with the segmentation. So this is, I believe it's taking like 100 point and it's trying to segment the stuff, and it's not doing too bad. So with this, we're able to, at a high level, just test out the input output and understand a bit how it's working. We're going to take a deeper look over there at the SAM automatic mask generator afterward. Once you have successfully ran the code, it's now time to map out the codebase structure at a high level. The quality of the codebase can really be felt in its overall architecture design. By mapping the architecture, you can get a better sense and appreciation of which area to focus on to truly understand the implementation. You'll also be able to get a better grasp at what type of researcher you're dealing with. If the architecture is kind of generally messy, you know you'll have to take whatever you find with a grain of salt and clean as you read. If the architecture is fairly clean, it usually means that things were properly trimmed down before the release. So let's check what they look like with SAM1. Okay, so here we are for a high-level overview of the infrastructure that we are dealing with. There's a bunch of stuff. If you know a bit programming and you've seen some codebase, you know where to look at stuff and where to just like disregard. This whole thing, I don't care at all. And then I know like I have these folders that have some importance, right? This one, most likely there's nothing in it. It's just like assets to showcase in the README. And then there's these things that are of interest. Let's look at each one of them. The demo folder is actually just like a web app demo in React. So we don't have to do much here. After that, you have the notebook section, and this is useful to get a sense of like how to use these things. So in this case, they put like all of their kind of tutorial stuff in there. So to understand how to do the stuff that we've seen previously, I was looking mainly at automatic mask generator example in this notebook. Then you have the script folder, and in the script folder, it starts to be important. There's two files mainly. There's this thing, and then there's this thing over here. This one is more important than this. We just take a note of it because when you look at the file, this is where a lot of the stuff to build the segment anything model are stored. After that, you have the main folder, which is segment anything, and in this folder, you have kind of a typical machine learning project type of structure. You have stuff that goes into modeling over here. You have a utility library over here. You have what's called automatic mask generator over there, build SAM, and predictor. We're gonna check each of these elements to understand a bit like how they are structured. So in the modeling folder, you have a bunch of files that correspond to all of the little building block that SAM is. So you have the image encoder that will be in there, the mask decoder code will be in there, the prompt encoder will be there. This should technically encompass all of these, right? And transformer should be inside over here. That should be the rough structure that we have. If you look back at the segment anything stuff, there's also the util folder structure. And then again, you have like AMG, ONNX, and you have this file that has like various transform that they're using. Careful here, we saw the same file twice. So we're gonna double check when we're gonna read the code if like we're talking about the util AMG or the script AMG. So at the high level, this is what's up. The most important part is really like everything that is in the segment anything folder. Overall, this is fairly clean. So this is also one of the reasons I took this repo to showcase this process. Usually it's not like that. Usually it's a bit more messy, but in this case it's a good one. Now that you have mapped out at the high level what's going on, it's time to elucidate each of the relevant elements by order of dependencies. Code in general, no matter where you're at, has quite a lot of abstraction layer and dependencies. Knowing how to navigate those is crucial. Deep learning code has the added difficulty of hiding a core concept between like subtle architectural design choice, which isn't obvious. Your knowledge from the paper will become very handy in spotting these regions and highlighting them for better understanding. To do so efficiently, I recommend starting from a top level component you work with and then finding a lower level nodes with low dependencies. These lower level nodes should be almost dependency free if possible, and you should understand what they do. Let's look at the SAM automatic mask generator for how this process looks like. We want to check out the SAM automatic mask generator thing. If you look back at our code, you see we have to import from segment anything the SAM automatic mask generator and the SAM model registry here. This thing is located over here. You see it in the init.py. We can see that we actually have it in the automatic mask generator file. So if we look at it here, this is where it's our entry point to the rest of the dependency tree for this code base, right? So if we land over here, then the exploration game, you have to see this really as a graph. The exploration game that you're doing at this point is you take the upper node where you actually interact with it to do something. In this case, like generating automatically a bunch of masks. And then you have to kind of explore, right? Kind of do a, depth first search to kind of find the nodes, right? And say like, oh, these are the nodes that like, they don't depend on anything. It will just tell me something. And then you go up the tree and you elucidate everything. The reason why you're doing it this way and not just trying to understand the top level first is like, look at this. There's all of these things that are being like abstracted away from you. If you have too much abstraction, when you're gonna read it, you're gonna feel its magic. And you're not going to understand it as much. So if we look in this, we have, we're stealing stuff from modeling, from the predictor thing, from utils.amg. So it's not the script, it's the AMG one. And in this, there's a whole lot of stuff that we're taking, right? But these are the three main files that or two main folder and files that we're taking our code from. So if we start with the modeling, we have SAM over here, right? And once you go into one of these files, you're gonna see this is like level 2, but in level 2, there's also other level. These dependency, you have the image encoder, the mask decoder, and the prompt encoder. So all of these three come up into to build up SAM, just like in the paper. If we go a layer down, now we're three layer deep. We're in the modeling, image encoder stuff, right? And we are doing still a bunch of importing. You see here we have from common, which usually common means like it's common from multiple file, kind of a like sub library that you're putting your stuff here. We have normalization layer and MLP block that we jam over here. If we look at the mask decoder, then we still have from common, we're using the layer norm 2D again. And from the prompt encoder, it's the same thing. We're still using the layer norm 2D. There's still other stuff we're using, but these is just it's not that important. These are just libraries that are away. I would limit like the tree of dependency to only the stuff that are new from the researcher. Don't go and like look under the hood how Torch is doing their stuff. Yeah. So here, common layer norm 2D. Now, so for layer deep, now we're like at the kind of at the lowest level, because if you take a look over here, oh, look at that. There's only the library stuff that we're importing and nothing else. So we hit one of our node. So if you read through this, right, and you understand what's going on, and you just take a note of it, and then you do the same thing here, and you take a note of it, what it effectively do is that now you're out of these things are magic and I don't understand what's up. I just take it as granted that they do work. And then you can bring this knowledge and this check mark to the layer above. So you bring it to the layer above over here. So it means that the prompt encoder, you have everything you need to understand it. Same thing for the mask decoder, you have everything you need to understand it. And for the image encoder. So these three, then you can go and then read them from top to bottom, understand what's up. And then you take another one, understand what's up, another one, understand what's up. You clear these up and then you can move a layer up again. So while moving a layer up, what you do, you go back to SAM and then you read it from top to bottom and you do a check mark on this. At this point, if you understood the image encoder, the mask decoder, and the prompt encoder, understanding this is just putting the stuff together. You don't have to, in your head, have all of the intricacy of the image encoder. You just know that it works and you understand the input output that we're using, and then you get out, and in the SAM you just take these for granted. Then we have the SAM predictor. SAM predictor, same thing. There's other stuff that are being used, but here we're importing the segment editing modeling. So SAM, we're importing this stuff, resize longest side. Shouldn't be too difficult, but like this is over there. So this is exactly what we saw before. So if you understood SAM, in here you will know what's up, right? You will know how it's used and how it's being leveraged. The only thing you have to double check is this one, which is in the utility AMG, and over here you're gonna read it. You see there's no dependency that is internal at this point, so all of these stuff are internal. So this is also a region where there's like lower level nodes that you need to get. Once you get that done, you move up a layer again, and then you finish the SAM predictor from top to bottom, you read it, and then you put a check mark. So you see, we kind of did like a first exploration, and then we cleared one node at a time, and then we continue our exploration. This is actually that first search. Finally, after all that, you will most likely hit conceptual knots that are unclear. Take note of them and work through them individually. One thing you have to understand at this point is that you're at the cutting edge. You're reading the literal implementation of a published paper that most likely only a handful of people on Earth understand at a deep level. Stuff might be weird, and some implementation detail might also be difficult to understand or slightly wrong. Don't beat yourself for it if it's hard. Take notes and study these points more deeply further. Now that we know the general flow we need to go through in order to map the codebase, let's tie everything together by doing a deep dive into the SAM1 paper. This analysis of the research and the code was made possible by following the framework I presented earlier. So it's a good way to see like what I synthesized from the full paper, which is like 30 pages long, into like the essential. Also, buckle up, we'll dive deeper into like 3 specific core components of the model architecture. This way you'll see how the flow work at a very low level. You'll see there's usually some challenges with such complex code. The methodology is segmented in 3 main areas: the task, the model, and the data. We're going to go through these along with the results and limitations of the original SAM technique. Let's get started with the task and requirements that the author used to design their segment editing model. So the other were mainly trying to develop a promptable model in there that was pre-trained on a broad dataset using like a task that enable generalization. You have the prompt, and then you have the image, and then you have the mask. Like that's kind of the rough idea. It always output the mask, and it can accept like a wide variety of prompts. So it can accept points in here. It can accept like boxes, so top left and then bottom right coordinate. It can accept literally another mask. It can accept text. So the idea is that you could give any of this, and then the model should be trained in a way that it will always output a mask. So this is very similar to how a large language model like generative pre-trained transformer have been conditioned. So with this setup, they can then have like a whole slew of downstream tasks that they can compose the model with. As you can see over here with all these like hand-picked images with the mask, we have a wide variety of masks of various sizes. We have over here the mask, the image with like less than 50 masks, so it's big, bulky masks that we're applying. And then you can get like up to the 1,000. Like look at this one. Like this one is absolutely crazy. And the segmentation looked pretty good. Same thing with this one. It's very, very fine details, and it still works. So this particular setup allowed the model to gain like zero-shot performance on multiple segmentation tasks without requiring any additional training. Like with the single point valid mask evaluation, like this was 0-shot on a new dataset. With the edge prediction, this is like a very old computer vision task. With the object proposal, it's a bit more mid-level. With the instance segmentation task. And finally, one that's a bit more experimental, which is the text to mask. So basically you input what you want to segment in plain English, and the model will like segment it properly. Now, the research motivation are all nice. This is Meta, so their research kind of need to be tied back to a business objective. So for this specific project, it's quite easy to see what it would unlock for a company like Meta that is so all into virtual reality. It's pretty interesting because their whole idea, and even throughout the paper, they mentioned this, it was to use SAM as a sub-module that was very reactive. A bit like the GPTs that are hosted by OpenAI and like whatever. They're very reactive. They can like almost be instantaneous. It's kind of the same idea here. Like they did the setup so that like they could host this and actually make it interactive with a demo of some sort. You can actually like just go to the demo and test it. This whole idea is, if you make sure that your infrastructure allow for this, now you can use that thing as a sub-module in whatever kind of bigger system you want to do. So it just happened that Meta is big on VR and AR. A model like this that is able to kind of segment anything and be prompted in different ways to do zero-shot task will be very useful in something like a bunch of rebands that you have that can understand what the heck is happening in your field of view. So yeah, good business move here. So to make this kind of financial model possible, there's a lot of structure that need to be put around the model so that it learn the quality of having flexible input and working well under uncertainty, like this one over here, where there's a dot that is put on the stuff. But what does it mean? Does it mean the whole like ostrich, just the top part, or just the head? You need to be able to work under these uncertainty. And similarly, to be able to train such a model, if you think about the generative pre-trained transformer, they have like internet scale amount of text data. They had to kind of build their own mass data set, and they were able to do it. And this is what the segment editing paper is not just about the model, it's also about like the data set. So they were able to generate 1 billion masks using like annotator that they had to pay, and then the model also was feeding back into the data, and then they were at some point being able to get to 1 billion masks to train their model properly. So before jumping into the model architecture, let's get a feel about like what SAM1 can do using its zero-shot capability on 2 tasks: automatic segmentation and single point mask generation. We're going to look at a bunch of code now. Here we are in the Collab notebook. This is not too long of a demo because I'm using a lot of the stuff that was in their actual GitHub in the notebook section. So, but I just like set it up on Google Drive so I can use it quite easily. First step, we mount the Google Drive, and there we're good to go. And then we can install the segment editing library here. So then I have this section where I'm going to actually read the two images. So one is me in a poster presentation and another one is me in a boat. So let's take a look at that. So this is me in front of a bunch of posters, and this is me on a boat. So the first thing that we're going to use segment editing for is automatic segmentation. So it needs a few things in there for it to work based on the repository. So it needs the checkpoint of the model. So I have this one that I downloaded from their stuff and I put into the Google Drive. You have to tell it what type of model you want, because you can have multiple model type and just where the device is in this case. So we're gonna do the SAM automatic mask generator, which will take an image and just like try to segment anything. So our mask generator is created here. So the model is actually loaded. So we have the model here, and then we prep it to do the actual task of like segmenting everything. Now we're gonna take our first image. So the first image was me in front of posters, right? So now we are generating all of the mask for that image. It's done in 11 seconds, so this is good. This thing is just to show the mask in front of the image. So nothing too crazy here, and we're just gonna plot it over there. If you run it multiple times, it will just be different, right? So here's the segmentation that it done. So it's not too bad actually, it's pretty okay, but it just like literally segmented everything in this stuff. There's hair that are well segmented, even though we have different type of hair. The end over here, our coat are segmented. Yeah, it looks not too bad. Now let's take a look at single point segmentation. So basically you put one point in there in the image and you try to do the segmentation. And in this case, you will segment with the ambiguity of the three parts. So you can have like the sub part, the part, and the whole. So this is just some helper function to be able to actually show the stuff properly in the image. But here we're going to take the SAM predictor. So this is another class from segment editing. And then we're going to set the image that we want to do the single point prediction on, and this one will be the boat one. And now here, this is where you're gonna say what is the coordinate of this point. If it was interactive, you will just click on it and then this will get like fed directly in there. But here, this is manual. And you're gonna see that in the result section for one of the tasks, the first one. So what do we need to segment if I select this? Is it the whole human? Is it just the t-shirt? Yeah, it's a bit ambiguous which part we should segment here. Let's actually predict that and see what the heck Sam can do. So then we can do this. This function is same thing as the previous one, just to show the mask properly. And there's going to be like 3 masks that we're going to show. So now we're going to iterate with the mask and the scores. And then we're going to just show like the proper mask and the proper score that it got. So let's take a look at this. This one, it got a good score, and you see, wow, look at this clean segmentation of the t-shirt. This is pretty good actually. Wow, I'm impressed. Then there's this one, the second mask. So this was the sub part, right? This is the part which is like, hey, let's actually segment the human. My hair seems to be something. And then like the whole part is, I think, the whole human. Yeah, that's it. So kind of makes some sense here. So anything that is extra to my skin seems to be this for the upper body. I don't know. Yeah. So this one is a bit weaker than this one. Yes, there you can see it in the score, right? It's more confident about this one, the only the t-shirt. This one is less confident, but still pretty confident that like, hey, I think you wanted to get the whole human. This one's like, I'm not sure, but I think like it's the t-shirt plus the hair of the dude. So that's that. This is how you use SAM at a very high level using the code from Meta. Now that we have a good feel about what SAM is trying to achieve and how it runs, let's take a deep dive at the model architecture. So the architecture kind of look like this. So you have your 3 main block that we're going to see in code soon. The image encoder over here, a prompt encoder over there. We have the code for that. We don't have the code for the text. We'll see why in a minute. And then we have the mask decoder, which is kind of custom because you need to be able to take the image embedding and the prompt encoder, which are By the way, the prompt are sparse with the points, box, and text, and dense with the mask. And they don't mix together, it's like separated, and then they're combined afterward. So the model resolve ambiguity by just like literally outputting 3 type of mask always. 3 was enough for most use cases, and then you get the score, and then they have like an IOU prediction module that will kind of estimate which one will be the best, and then we'll output only that if needed. Otherwise, we'll always output a 3. So, interesting part, all of these elements, like they're not all novel. Like this part is absolutely not novel. It's a vision transformer, so the H version. This part also is not that novel, especially the clip part, which is the text encoder. The mask decoder is kind of novel, but not that. It's just a transform version of another step. The novelty in this whole thing is really reside on how they set up the infrastructure and then the training procedure, like the generative pre-trained transformer, to have this kind of emergence of zero-shot capability. So if we look quickly at each of them, so the image encoder is a VIT, like I said, it's a mask autoencoder. Nothing too crazy here. The prompt encoders has like really 2 parts, so the dense part and the sparse part. And the interesting part here is the dense part with the mask that it output is really useful when you have to kind of compose SAM with multiple other model like a VIT-H, and they're doing this in the instance segmentation. And then there's like the mask decoder in the appendix to go into more detail about the structure, and we can see that in the code how it's made. But they base this thing into the like transformer decoder block, and they have a modified dynamic mask prediction head that use the prompt self-attention also, and cross-attention to update like all of the embeddings. There's also an NLP that is used to output the token to a dynamic linear classifier. So this is tasked to computing the foreground probability at each of the image location. So at a more granular level here, the loss that we're using is there's a focal loss and dice loss at a 20:1 ratio. And the focal loss is designed for like extreme class imbalance, like when you have a lot of background point and very few foreground point. So this is during the training. And then this is effectively just like a modified version of cross entropy. Then you have the dice loss here, which is defined as 2 times the area of overlap divided by the total area. The idea here is like for the dice to put more weight on the right overlap region. So the training algorithm is very crucial and central. It's a central piece of the whole thing because this is how they like mimicked the generative pre-trained kind of setup. It's doing the same thing as when an annotator will do interactive segmentation. So there's a bunch of more detail about it, but like that's kind of the gist of it. And then the actual training recipe, they use AdamW, they regularize SAM with like the weight decay to 0.1, and then they apply drop path. So there's nothing too crazy here in the actual training of it. They use GELU in most of these of the network also. All right. So let's take a look at the main architecture code for SAM and its 3 main components. So I'm going to break down the 4 main blocks in the GitHub repository, and we're going to see like how they are all connected together. All right, so the whole code is over here in the segment anything thing. And if you can see here, there's a subtle link to go to segment anything too. But what we're gonna take a look here today is mostly over here in the modeling section. We're gonna look here mainly at SAM, the prompt encoder, the mask decoder, and the image encoder code. I just split them up and then I put them into like a whiteboard type of application. But we're mainly gonna go over here and start at them one by one. So let's take a look and zoom in into SAM. At a high level overview, SAM is kind of a wrapper class which will encompass the image encoder, the mask decoder, and the prompt encoder, and it will compose them in order to kind of do the output. You see SAM, the class, doesn't have much because all of the stuff is happening in the other modules. So the constructor is kind of straightforward. We're just gonna have these 3 main blocks, and then we have these for the normalization that we need to do on the image to resemble how it was done during the training. But there's absolutely nothing of interest in the constructor. Everything is happening in the forward function. If we just take this out, right, and we look at the input and the output of the forward, it will make more sense what the heck is happening in SAM. This is SAM. So you have the image, it goes into the image encoder, and then you have a whole bunch of stuff that happens. You have the prompt encoder here, the mask decoder, and then we have that output. This is like visually, so in data structure format, the input and the output will be defined like this for this whole thing. The input is over here and it goes into SAM, and then SAM does a bunch of stuff and output this stuff. So what does it do? It's predict the mask end-to-end from provided image and prompt. If prompts are not known in advance, using SAM predictor is recommended over calling the model directly. So SAM predictor, we saw it in the code stuff that we've done before. Just a wrapper on SAM. This you don't need to know. Let's take a look at the input. We have all of these, and the important part is it's basically this whole part over here, from here to here. It's a list of dictionary. Each index is an image, so you can batch them, and then the dictionary is what are the input that you're giving for the specific image, and they include the image, right? So I took it out here. So first you have the image, which is the tensor. You have the original size of the image that you're giving also, because SAM will like kind of downscale it and then upscale it so that you can slap the mask back on. You have these four that are kind of optional. So here you have the point coordinate if you're doing like single point stuff. You have the points label. You have the boxes prompt, so upper and lower corner, and then you have the mask input if you're composing the stuff, like in the instance segmentation thing. And here you're saying if you want to output multiple masks or not. By default, you will do. That's the input that you're giving, and this dictionary for one is one image. And then you can have like however image you want to batch. What it returns though is also a list of dictionary, and a dictionary will have multiple things, 3 things. So it will have the mask. So here is like there's a bunch of masks that will return to it. Always return the mask. So IOU prediction, you get that, and the low res logit, you also get that. This is for these core if you need them, and this is for the logit that can be passed as a mask to other iteration in another sub module if you need to compose stuff. So if we go down a bit, we're going to do preprocess on each of the image, and preprocess is simple. It will just take like the pixel mean and pixel standard deviation to normalize the color to look like what was there in the training data. And then here we're just doing some padding so that everything kind of looked the same. That was pre-processed. And then we're doing image encoder, and we're putting the input image in there. And then we get our image embedding out. So this is effectively like this part that we're doing. So this image encoder stuff is a vid.h, and it's generating the embedding. We're gonna dive into it, but not in very much depth, because it haven't changed much. So if we continue here, we are running this across the image and the embedding, right? Because we're batching the stuff. So if there's point coordinate in the stuff, we're gonna get the points. Otherwise, there's just gonna be no points. And then we're gonna take the whole thing and jam it into the prompt encoder. Everything we have, points, boxes, and mask, we give it to the prompt encoder, and then the prompt encoder will kind of figure how to wangle the sparse and then the dense embedding. So this is what we get out, sparse and dense. So this is this part, right, over there. We've done this part. And after this point, we're gonna do the mask decoder. We're gonna take like everything that is our current embedding, the prompt encoder, the sparse embedding, all of this, and we're gonna give it all to this thing. And then it will go here, and then it will go through this complicated flow to output the mask, the IOU score over there. So this is what we get out, the mask and then the IOU. Here this is low resolution, and we're going to post-process them to upscale them back to what they were supposed to be. So this is the post-process mask, which is over here. You give everything. So remove the padding and upscale the original image size to interpolate function call here to do just that, to remove the padding and then to upscale them. And that's that. And after that, what we're doing is we're thresholding the mask, right, with this mask threshold variable, and we just output that in a dictionary. You see, we have the output here. This is a list like that. So this is how we output the list, and we go and iterate into one image at a time. Let's take a look now at one of these components. First one we're going to take a look at is the image encoder, and the image encoder, like I said, is just like straight up ripped from another part. So it's in this this backbone over there in the Detectron 2 repository. So literally took it, modify a bunch of stuff, but not too much, and then just jam it in there. So if we see over here, this is the image encoder vid class, and there's a whole bunch of variables. Most of them are already like pre-put. There's not that much that we need to know. The activation layer is all JDO. We have the normalization layer that we're using. This is another utility class, but like it's not that important. And all of these parameters match what is supposed to be based on the data set that they're running with. So here they're constructing the network, and it's fairly straightforward. You have the patch embedding over here, and then if we're using the position embedding, so initialize them, and after that it's actually building the network. So we have these block stuff, which are the transformer block that were needed here. And then you have like the sequential head. There's two convolution that we're doing. Convolution, normalization layer, another convolution, normalization layer. And then we're kind of done. And the forward is also very simple, right? So you're getting the embedding, you're adding the positional embedding back, and you iterate over the block, transformer block, and then you just get out and then do this last part with the convolution layer. So then we're going into the prompt encoder, bunch of parameters to start with, but most of the action is happening here. So this is the position embedding layer that they're going to use. This is for the point embedding over here. There's this embedding for when the point is not there. Here you're using the same trick again when there's no mask added. And then here this whole stuff is to downscale the image, not the image, the mask, just so that they match. All right, so let's take a look at the forward. In the forward here, we're gonna like embed the different type of prompt, and then we're gonna have two classes. We have the sparse embedding and then the dense embedding. Dense is just the mask that we're gonna return, it's denser, and the sparse is the point boxes and text, but text is not added in this. And that's that. Like if there is a point, we're just gonna jam the coordinate, the labels in there, and our embed points, which will create an embedding, put it over here, and then we're just going to concatenate it to our sparse embedding. And if there's box, we're going to do the box and then just embed it. Nothing too crazy. Mask is the same thing. If there's no mask embedding, we're just going to like use the no mask embedding that we've created over here for this specific purposes. And we're going to return both of them over here. So embedding, like if you don't know, you should know, but if you don't, so you take something like this that can have a lot of degree of freedom of stuff that it can, how it can be represented. It's that in this case it's a text, but it can be like a mask, it can be like points, and then you find a representation that is in a set dimensional space. In this case it's let's say you don't have that, it's 3-dimension and it's a vector. So this vector now means angry. So we can go into depth into like what's happening in each of these, but it's not that relevant. You just understand that like for each of the different type of input prompt, they will put them into like a vector space that makes sense for them. Sparse and dense are separated, and here we're just jammed when we call embed mask, we actually just call mask downscaling, and we pass through the network we saw earlier. So yeah, the text stuff is not there, right? So I checked and I was a bit confused, and I knew it was using clip, but I thought it would like, I don't know. I actually didn't know what to expect there, but they just didn't add it into the stuff. It's not publicly available. I don't know why. It's a bit weird. Like I think kind of sucked a bit. It was not that performant, but it was cool, but not that performant because they just give one example and like get it wrong. So we have whale, a beaver, tooth grill here, but then when you say wiper, it kind of just doesn't know what you're talking about for this specific image, and you have to click and give a point. So I feel like that specific portion was not as mature and it was not working that well.
So this one, yeah, I have to buckle up a bit because it's not the cleanest one of the three, right? It's the worst. There's a lot of layers of complexity in there, but we're gonna unpack it step by step. So here you have the class, the mass decoder class. There's a bunch of variables that are of our interest, especially this one, the transformer one. So you see transformer, it's a module, and then you see it being instantiated here. Self.transformer equal transformer. If you look in here, right, at the top of the file, there's nothing that is being imported here, which I think is a big mistake. Note that, because we're going to go through like the higher level code, but then we are going to have to do a bit of a detective work here to find where the transformer is at. You have the rest is we're just instantiating the embedding for the output. So there's nothing too much here. Here it's the output scaling, that thing, this comp transpose 2D and then comp transpose 2D again, is this part of the drawing over here. And then we have this hyper network over there. It's an MLP, right? And it corresponds to that part here. This one, the IO prediction head, is just one MLP and it's over there. And this one is to estimate the IO score so that we can sort the stuff. So we have these three components. In the forward function, we'll most likely work with this part here. This part, the rest is a bit hidden. We'll dig it. So if we look at the forward now, so you have all of these as input, like we saw in the previous call. It's a bit of a weird abstraction. I don't know why they did that. Maybe they reused some part, say the predict mask somewhere else, but nothing is happening here. There's just a predict mask function, which you give everything, and it give you the mask and the IU pred. The predict mask corresponds to this whole orange box. This whole thing is the predict mask. And then we can do correction if we want to output one or multiple mask. And all of this is being outputted here. Everything is happening in predict mask. So you see already we're starting to go a bit deeper. So this is predict mask, and it's a bit of a mess, to be honest. Here we have the output tokens. So this is these ones over there, the output tokens and the prompt tokens that we need here for the IO token weight. So this will correspond to the like output token over there. So we concatenate all of them together, and then this is this input. The image embedding is here, right? This corresponds to this, but we need to kind of rework it a bit. So this is what this part is doing. It's reworking a bit dimension. These things, so the SRC and the position SRC here will be given to that dotted line setup. Anyway, so we give the SRC and poster SRC and these tokens, right, which are these input to a transformer, which is what we saw before. And this will return two things. It will return this and the SRC. This is, it's over here. This is the SRC, right? The how is it called? HS is here. It's already weird because this thing returned two things that are being the output of different elements in the same architecture. A bit weird, we're gonna dive into it a bit, but then you take these out, the IO token, the mask token, and then we follow like the rest of the stuff. So this SRC that we've talked about, this one will get put into the output scaling. The output scaling we already talked about, it's this one. And then that part over here, this whole thing there is what's happening on over here. There, and then this part here is our dot product per mask. You see we're looking at the upscale embedding, which is gotten by shoving SRC in the output scaling and getting the upscale embedding back. And then we do the dot product with the hyper in here, which is when you shove the mask through this network. And finally, the IO prediction head is pretty easy. It's this IO output token, and we are able to create the score here. You see these two things, output token per mask and IO output token, they are within the HS variable that we've talked about, and that is being sorted out over here. Now, most of the important stuff is not being mentioned here. It's just a transformer. So like we saw over here in the mask decoder, there's no transforming being added. So you have to dig a bit. And once you dig a bit, you realize that it's in the init.py of the modeling folder. It's still valid. It's still okay. It's just a bit weird. It's just a bit weird to do it like this. There's a file called transformer, which hosts the two-way transformer. That thing is what's being used as a transformer. Init.py will import all of this in all of the file when we're running it. So this is what we're looking for. So you have to take a look actually at the transformer file here. And in the transformer file, this is where we have like the right information about this last bit that was kind of hidden. So the two-way transformer, we get the MLP block and whatever. And then here, this is how it's set up. If you dig some more in another file, in the build section, there's something called build SAM. And when you look at it, this is like a way to like build SAM, because you're gonna give it explicitly which part that you want, the image encoder, the prompt encoder, and mask decoder. And over there, then you start to see what's up. So the parameter that is important, depth, has a depth of 2, because it's like the 2 block that we saw times 2. And then you have the other variable that are being set. Now, when it's going to be created, it's going to be created properly. And when you're going to pass the parameters, it will go in the forward properly. Just on the side. So if you look at this and you see no default parameter, don't freak out. Now we're over here, right, in the two-way transformer. And now it starts to make sense, right? So this is 2. The depth, because we're doing from I in range depth, and then we're doing 2 times this. So this is why there's a explicit 2 in here to match this 2 over there. That part, we're gonna go through it in a bit. But this part, the final attention token to image, is this part. If we go a bit down in the forward, here's what's happening. We're very deep now, and it starts to get a bit abstracted away what's happening. But don't worry too much. Here we're just normalizing a bit the format of the stuff. There's 2 things that are important, the queries and the keys. The queries are these output, and the keys, these output that will be out over here, right? So we're putting the queries and the keys, which are the point embedding and the image embedding. So the keys are the image embedding, the queries are the point embedding, and then we're gonna shove them through the layers. So through this layer over here, there's 2 of them. You see the keys get changed and the queries get changed. Now, that's this part, right? This is this part. So this part over here only get applied to the queries, actually. If you follow this part, we're changing a bunch of stuff over there. And then we're running the final attention token to image, and we're passing the Q's and the K here. And then we're passing also the keys over there. And if you take a look, we are changing the queries here. The queries get modified, and only the queries goes through the final normalization layer. So the queries get overwritten on this final layer, but not the keys. The keys are the same as these ones. So this is how we get the keys, which is the src variable at the top that we saw, and the hs variable kind of separated. We overwrote this when it went through this, right? We overwrote it, but here we didn't overwrite it. We just returned it as it's skipping this final step. Now, this layer, let's take a look at it. This is a two-way attention block, and if you take a look, we have the attention. You can dive to how attention is set up, but this is fairly standard. So there's an attention block over there. And then we're naming really well the stuff. So here, this is a cross attention token to image. This token to image is this one, right? And then we have our self attention here. This layer is this one. Then we have normalization layer. We have our MLP block over there with normalization layer. And then we have our cross attention image 2 token. So this one is here. Remember, this is one of the block. There's actually 2 of them when we're out of there, but here there's only 1. And if we look at the forward, also pretty standard. We're taking the queries, which is the purple thing here. So like this is our prompt stuff that goes there, and then this is our keys that are going over there. So this is cross attention block. So token to image is this one, and you see we're giving the both the keys and queries over here. And then the self-attention, we have given it over here or there, depending if we skip layer, whatever. So this is happening over here. There's no key that is being added. MLP block, this is happening here. And then cross-attention image token, this is happening over there. And that's it. This madness stops here. But you see how deep we had to go to just go back all the way up over there in this transformer thing. Honestly, this predict mask, we shouldn't have needed that thing, right? Depending, I don't know, I didn't dig deep enough. Maybe I'm wrong, but like this layer of abstraction for me is absolutely useless. It should stay in the forward and be jammed as is, because then we're too deep. The second thing I think they should have done is actually just import the thing in there. Worst case, you import it, and now it's just more clear. It's a two-way attention thing versus just like it's just transformer that is being mentioned here. The third thing that they did wrong, well, not wrong, but I mean they could have done better, is on this part, like just put some default. They were doing it in all of the other thing. Just put some default that look like what you said in the paper. Yes, maybe like you need to change some stuff depending on the experiment that you were running. But if this is like one of the structure for the paper, and then it's literally a figure that you're having that is this, please do put it as a default. It will be easier to follow the flow because I had to do like some intense detective work to be able to figure out what the heck is going on. Anyway, that's the mass decoder. So now if we come back all the way up to Sam, when we do mass decoder, we did all of this stuff. When we do prompt encoder, we did all the stuff that we saw. And then when we do image encoder, we did the vid stuff that we saw. And we just compose all of this together and then we shoot it back to the output. Now that we have a solid understanding of the internal architecture, let's take a look at the other important part of SAM, which is the data. Datasets wise, SAM 1 is absolutely massive. So it's order of magnitude greater than like the other mass dataset. So you see here we have 11 million images. And then you see the other ones, like there's just open image that get close to the number of image, but mask wise, it's order of magnitude greater. 1.1 billion masks for 11 million images. And if you see here, there's generally more masks per image with SAM. So if we look at the percentage of the image that has mask, we see it's not like super bulky ones. It's a bit more precise, less bulky than the other ones. And if we look at the percent of a mask that has like very high complexity, it's like similar to other dataset here. And by the way, the dataset is open source, so that's pretty cool. So if you want to take a look at it, you can take a look at it in the website. How they were able to train something like this is very interesting because they leveraged the model itself and human annotator to build up an actual dataset. So the first stage here was assisted and quite manual annotation. So it was just to build the initial dataset needed for the next stage. So this is purely classical assisted segmentation methods, nothing new here. The second stage is where it gets interesting because the model at this point was good enough to get the big mask going in each of the image, but the author wanted to add a bit more diversity in the type of mask generated. What they did was a semi-automatic stage where the annotator had to fill up the rest of the smaller object that were not detected by SAM, which was pre-filling all of the image with like the big mask. During this process, they retrained the model multiple times, so it got better and better. So at this point in time, they had like millions of masks already built up, and then they retrained SAM1 on all of this. In the third stage, they just let loose the model completely on the whole dataset and generated billionth worth of masks. This was feasible mainly because at this point in time, the model was good enough and it understood ambiguity because of its architecture. So using no maximal separation and other thresholding technique, they were able to gather like the most confident mask on all of these 11 million images. And in each of these images, there was like quite a lot of masks. And this is how they got a billion masks. With these three components working together, the other were able to create that financial model. Let's take a look at the result now. First one we got is the zero-shot single-point valid mask. This one is difficult because the answer is very ill-defined. It's a single point. There can be multiple answers to that point. The author tested their performance of their model on 23 dataset, which did better in 16 of them. Interestingly, when they ask human annotator to rate the mask, those of SAM1 are always coming on top, just below the ground truth. Another cool thing is that SAM1 is better than other algorithm when there's a lot of ambiguity involved. With 1 point, it gets consistently better result across dataset. Next up, we have the classical task of detecting the edges on an image with the BSDS 500 dataset. Reminder that SAM is simply being prompted properly in here to be able to generate the right output. So specifically, they prompted SAM with a 16 by 16 regular grid of foreground points. They removed the random mask, use Sobel filtering to unthreshold the mask probability map, and then they do some other post-processing to get the final result. And if you look in the image, it does look qualitatively good. SAM is not the best in this specific instance, but is the best of the zero-shot transfer method. A reminder here that SAM never saw the image in the BSDS 500 dataset compared to the state-of-the-art. Afterward, we have the classical task of object proposal. The visual transformer .h version is obviously better than SAM since it has been trained on the Elvis dataset in this case. The other are hypothesizing that it has learned the idiosyncrasy of the data while SAM didn't have access to it. What we mean by that is all the little details that will game a bit the performance metric. Interestingly, SAM is doing quite well in medium and large mask. It's really in a small object to detect that it struggled a bit. Next up, we have the instance segmentation task where we're trying to make a pixel by pixel segmentation map of everything in the image. So basically segment everything. The method is interesting here because it uses the same combination methodology that we see in systems like DALI with a clip model inside. So here the vid date is prior to being fed to the SAM model. You can appreciate qualitatively how SAM is able to improve the quality of the segmentation based on that vid.h mask input. Quantitatively, again, a trained vid.h model on the Elvis dataset does better than just SAM, but when the human annotator look at the quality of the mask, SAM look better and closer to the ground truth. Finally, the other did something very interesting where they tested the zero-shot performance of SAM on a novel task of text to mask. There is no quantitative result here, just a qualitative one, and we can all admit like pretty cool. The one thing that is interesting here is that when there's a mix of text plus point, the model is improving quite well. So result-wise, we see that SAM has some interesting zero-shot performance. However, there are some limitations with this first iteration of the segment editing model. So as explained by the other himself, like it's not perfect, can miss fine structure, hallucinate small disconnected component. It's not as crispy as other more fine-tuned method. They are saying themselves that there's room for improvement in the general architecture, but also generally just the performance of the model. So with more effort on this front, this whole technique can be much improved.
And that's it. With these, you have everything you need to start digging into cutting-edge deep learning research. After that, it's like any skills. You read research that is the most relevant for your field and improve over time. Don't hesitate to leave a comment if you have any questions. I'll hang around a bit and try to answer as much as possible. Have a great week, everyone, and see you all in the next video.